In this video, we're going to discuss line integrals, and specifically, we're going to practice finding a piecewise smooth parameterization of a plane curve or a space curve C. Then we're going to evaluate the line integral of a scalar function. We'll do line integrals of vector functions in the next video. And to motivate all of this, we're going to find the mass of a wire. So here's the idea behind line integrals. Rather than integrating over an interval from A to B on the x-axis, we're going to integrate over a curve. Yes, the name is not a great name. I guess it should really be called a curve integral, but that's okay. We'll stick with line integral. That's a standard terminology, but really what we're doing is we're taking a function that's well defined on some curve, maybe in the xy plane, or a function that's well defined on some curve in three-dimensional space. Actually, it would work just as well in n-dimensional space. And we're saying rather than integrate over an interval on the x-axis, let's integrate over that. If you're thinking, why on earth would I ever want to do that? Here's one, what seems like a somewhat contrived application. Say you want to find the mass of a wire. And you know the density of the wire is given by f of x, y, z. So this is a wire of variable density. Every point has a little bit different density. So that's why we're saying that it's a function of position on the wire. And this is mass per unit length. Well, if I want to find the total mass of the wire, all I do is I take that wire and I break it up into n little pieces. I feel like you've done this before. It's because you have done it many times before. At t equals a, we're at that location, x of a, y of a. At t equals b, we're at x of b, y of b. Actually, I guess I'm using my 2D example, so I'll make this just a function of x and y instead of x, y, and z. Well, then the mass of one of those little pieces is just the density of that little piece, mass per unit length times the length. So if I'm on the ith piece, that density is approximately constant on that piece because it's so small. That constant density is just given by f of x sub I, y sub I. That's just your density function evaluated at some point on the interval, times the length of the piece. Now we could call that delta s sub I, where s is that arc length that we talked about earlier. Now, of course, if I want the total mass, I just add all of those other masses together. I've got n of them. Say I don't want to have to write out all n of them, so I use sigma notation. End up with something like this. And then if I want the exact mass, under some circumstances, and those circumstances are that our curve C is a piecewise smooth curve, then what I get is the total mass is the integral over C of f of x, y ds. Now this is not particularly useful. It's probably got too many variables. I've got a curve C, I've got x and y, and I've got an s. I'd really like to tie all of these together somehow. We'll tie all of those together in just a minute. So that's our one contrived example of what this is useful for. There are lots of other things that it's useful for, but we're not going to talk about those in this class. But this line integral, it's that same idea. We're taking a function, we're evaluating at a point x, y, and then we're multiplying by a tiny length. It's like a weighted average. And we're adding all of those together, and we're saying we have infinitely many pieces, so it's an integral rather than a finite sum. So that's if our curve is in 2D. If our curve is in 3D, we would define our line integral this way. Oops, that should be a Z, not an S. Okay, so this is the definition, and that's the idea, that's where it comes from. But I never use these formulas. They're pretty worthless. In order to be able to evaluate this, I need some variable to tie all the other variables together. Well, if we're on a piecewise smooth parameterization, there is a variable that ties everything together. We can just use the variable t. While I'm on this curve, x is equal to x of t and y is equal to y of t. So I could write f in terms of t by replacing x with whatever x is in terms of t and replacing y with whatever y is in terms of t. And this ds, well, that's an arc length. Well, we know how to find the arc length or the length of a parametrically defined curve like this. So we can substitute that and write that in terms of t as well. So we're not going to use these, we're going to use these. So we're assuming that we have a piecewise smooth parameterization of C. And I'll remind you what piecewise smooth means in just a moment. And that's piecewise smooth parameterization is given by R of T. In that case, then our line integral of f of xy over C is given by this. And I guess we need some bounds for t. So C is given by this piecewise smooth parameterization, and t starts at A and ends at B. Then I'll integrate from t equals A to t equals B. So that's from this initial point on my curve to the terminal point on my curve. It's not really initial point and terminal point in the same way that we use it for vectors, but you get the idea. We're going to start here, we're going to end here. And then I need that one variable to tie everything together, and that variable is t. So I replace x with x of t. I replace y with y of t. And for ds, a little bit of an aside here. Do you remember when we defined S, the arc length parameter, when we studied vector valued functions? We said S of t was the integral from a to t of the magnitude of r prime of u du. And this actually made a lot of sense if we were thinking of t as a time. This is saying, take the velocity and then integrate it. And integrate it over an interval of t values. So this is the magnitude of the velocity, so that's speed times time. What do you get when you multiply speed and time? Well, it's just distance. So I've got a little tiny distance, and then I'm adding those up, and that's going to give me the total distance, or the total length along the curve from t equals A to t equals t. Now, if this is our definition of S of t, been a while since Calculus 1, but in Calculus 1 we learned, due to the fundamental theorem of calculus, if I take the derivative of this integral, all I end up with is that integrand, except instead of having a u there, I'm going to have a t there. Actually, this makes a lot of sense. This is instantaneous change in distance per unit time as magnitude of velocity, which is speed. Yeah, change in distance per unit time should be speed. That makes sense if t is a time parameter. And then ds is defined to be the derivative of s with respect to t times dt. So again, this does make sense because it's a tiny distance, and we're saying that tiny distance is equal to speed times time. So ds, if I want to write it in terms of t, well, I can just replace ds with speed times time. So that's if f is a function of 2 variables. And if f is a function of 3 variables, we do the same thing. You integrate from t equals a to t equals b. Then remember, while you're on this curve, x is given by x of t, y is given by y of t, and z is given by z of t for some value of t between t equals a and t equals b. So you can replace x with x of t and y with y of t and z with z of t, because while we're on the curve, that's exactly what they're equal to. So now my function f is written entirely in terms of t. We're integrating from a to b, and ds is again that magnitude of r prime of t times dt. So if t is a time parameter, this is speed times time. Makes sense. Little tiny distance is the same as speed times time. Okay, so these are the forms that we're going to evaluate. This is a definition. It's not particularly useful, but it tells us what we're doing. We're taking this function, we're evaluating it, and we're multiplying by a tiny length. We're adding those up, and we're getting mass in our one contrived application. But this is actually how I do it. I write everything in terms of t, and then I just integrate. Okay, so to evaluate this, we'll need 2 things. The first thing we need to do is find a piecewise smooth parameterization of C. Sometimes that's given to you. Sometimes people just give you R of T in the interval from A to B. Then you're all set. All you have to do is recognize X of T and Y of T, possibly Z of T if you're in 3 dimensions, and then substitute everything in. It's just a substitution method. It's pretty simple. Now, if they don't give you the piecewise smooth parameterization, you have to find that yourself. And again, I'm going to remind you what that is in just a second. And then once you have your piecewise smooth parameterization, and you've got this interval from t equals a to t equals b, so you've got x of t, y of t, potentially z of t, and all of these values, you just substitute everything in, and then you evaluate the integral. And then it's just a regular integral. It's a calc 1 integral in terms of t, no big deal. Okay. Now, for students, I will tell you that almost everyone struggles with this piece. Out of this 3-step process, finding a piecewise smooth parameterization is probably the hardest part for most students. So we're going to focus on that, and then we'll evaluate some integrals. Okay. Now, before we do that, let's talk about what a smooth parameterization is. We say that C is a smooth curve if it has no sharp corners. So here's a curve that's smooth. That's not smooth because of that corner there. That's not smooth because of that corner there. Now, if I don't actually have the graph of it, I need to be able to infer what the graph looks like given a parameterization. Let's say you have R of t and you want to know, does the curve look like this or does it look like this? Is my curve smooth or is it not smooth? Well, then I just take the derivative of each of the components of R. If R prime of t is not equal to the 0 vector, and remember what that means. That means x prime and y prime if we're in 2D, or x prime, y prime, and z prime if we're in 3D, are not simultaneously 0. Then the curve is smooth. The curve, which could be a plane curve or a space curve, is smooth. Now, if x prime, y prime, and z prime, or x prime and y prime if you're in the plane, are simultaneously 0, you could have a sharp corner like this and like this. But don't worry, it actually turns out to be just fine. This one is smooth. This one is not smooth, and this one is not smooth. But these are called piecewise smooth. And it turns out that's all we need. These are just smooth in pieces. Say, well, it's not smooth the whole time, but it's smooth on this piece and it's smooth on this piece. That's all I need to be able to evaluate these integrals. We need to have a piecewise smooth parameterization of the curve. So I have some function R of t for this part and maybe a different function R of t for this part. And then we put them together as a piecewise function, and we call that the parameterization of C. That's going to be good enough for us. So this is piecewise smooth, and this is piecewise smooth. So that's okay. We just end up doing the integral over this piece and then the integral over that piece and adding them together. Same thing here, integral over this piece and integral over that piece and adding them together. So we're looking for a parameterization. Now let's say this is our piecewise smooth curve. Or actually, I misspoke. Let's say that this is our curve and we want a piecewise smooth parameterization of this curve. Okay. So maybe I've got a function that looks like this. So there's part of my curve C, and there's part of my curve C, and there's another part of my curve C. And this is the square root function, y equals square root of x. This is x equals 4, that's y equals 2. And our parameterization is being traced out in this direction. So as t increases, we go this way, and then we go down, and then we go over this way, and then you could repeat. And let's say we're trying to find a piecewise smooth parameterization of C. Well, first I notice that I'm in 2D. So my parameterization is going to have two components, x of t and y of t. But I also notice that I've got 3 smooth pieces. I've got a smooth piece here, a smooth piece here, and a smooth piece here. So it's actually going to be a piecewise function. It'll be given by r sub 1 of t, or t on some first interval. I'll probably start with t equals 0 and go to b. And then I'll call this r sub 2 of t for my next interval. So let's start at b, pick up where we left off, and then go to c. And then we've got r sub 3 of t on the next interval. We're going to go from c to d. And with those three pieces together, we're going to be able to trace out this curve. So our goal is to find R1, R2, and R3, and then we'll put them all together. And this will be our piecewise smooth parameterization of C. Okay, so let's focus on R1 of T. And let's let R1 trace out just this piece. Well, R1 of T is going to be given by X of T and Y of T. And I'd like T to start at 0, and it's going to go to some value. Now, since X goes from 0 to 4, if I let T go from 0 to 4 and I let X equal T, well, that should work. Because as T goes from 0 to 4, X goes from 0 to 4. We're good there. Then if I want to find Y of T, I just have to remember that Y is the square root of X. If X equals T, well, then Y is just the square root of T. So we've got that right there. Now you can use less than or equal to or strictly less than, it doesn't matter. Either one is fine. Okay, so that's our first piece. R sub 1 is related to that part of C that is part of the square root function. And R sub 2, let's let R sub 2 be this one, correspond to that piece. If I want, I could call this C sub 1 and C sub 2, and I could call this curve C sub 3. And C, we could say, is the union of C1, C2, and C3. It just means you start here and you keep going, okay? We're in the plane, so R sub 2 is going to have components X of T and Y of T. Now what I'm about to do is not necessary, but I like to do it this way. I like to think of us tracing out this curve like a particle that's traveling along this path. If I've got a particle traveling along this path, at time t equals 4, that particle is right here. I'd like to pick up where I left off. So I'm going to start with t equals 4 and go to some other value of t. And then I just look at this line segment. And if either of my variables, x or y, is constant, like that's the easy part. I fill that in first. Well, I notice on this line segment, x is equal to 4. So I can replace x with 4. And y is decreasing, and y goes down by 2 units. Now remember how we said, let's let t go from 0 to 4 and let x be t, because x was going from 0 to 4 at the same time interval? Since we're moving 2 units in the y direction, I'd like to go at a speed so that we're covering 1 unit for every unit time. And let's let t go from 4 to 6. Then to figure out the function for y of t here, I'm just going to set up a t table, and I'm going to think of a linear relationship between y and t that will allow me to start here and end here. So at t equals 4, we're at this location, and at t equals 6, we're at this location. Excuse me. So t goes from 4 to 6, and y starts at 2 and ends at 0 on that little line segment. Now, if you do what I just did, or you see that that's a y changing by 2 units, so you let x or t change by 2 units, then when you make this t table, you should be able to add these two together and get a constant, or subtract these from each other and get a constant. And that's going to be a very simple way to get the equation of that line, that linear relationship between y and t. It's not the equation of that line. We're just finding a linear relationship between y and the parameter. So as t increases, y is going to decrease to 0. Well, I see right away 2 plus 4 is 6 and 0 plus 6 is 6. So it looks like y plus t must be 6. And I need y as a function of t. So I'll let y equal 6 minus t. Cool. All right, now let's find r sub 3 of t. The parameterization for that third part of c, which I'm calling c sub 3. Since we're in the plane, r sub 3 has components x of t and y of t. And again, I'd like to pick up where I left off. T starts at 6. And x goes from 4 back to 0. So we move 4 units in this direction. So let's let t increase by 4. Let's let t go from 6 to 10. And because this is the last piece, let's make it less than or equal to 10. Okay. Now, if x or y is constant, it's always easiest to fill that in first. And this time, hope you guys all see that y is equal to 0 the whole time. And x is changing. So y is 0. And x, we want to be a linear function of t. So I'll put x here and t here. As t goes from 6 to 10, I'd like x to go from 4 back to 0. So t equals 10, we're right over here. So x starts at 4 when t equals 6 and ends at 0 when t equals 10. And then I look at this again, I say, hey, 4 plus 6 is 10, 0 plus 10 is 10, so x plus t must be 10. So x is 10 minus t. Okay, so now we've got a piecewise smooth parameterization, almost. We've got all the components of it. R of t is t times I hat plus square root of t times j hat, for t on the interval from 0 to 4. And 4 times I hat plus the quantity 6 minus t times j hat on the interval from 4 to 6. And then we've got 10 minus t times I hat plus 0 times j hat on the interval from 6 to 10. And that is our piecewise smooth parameterization. Now let's say that this is our curve and someone asks us to evaluate this integral over the curve C. So someone says, okay, evaluate the integral over C of 3 times the quantity x minus y cubed ds. Well, in order to do that, you need to write everything in terms of t. So you need this function written in terms of t, and you need ds written in terms of t. And when we say the line integral over c, we're going to start at some value of t and go to some other value of c. Or some value of t and go to some other value of t, excuse me. So our curve C looks like this. And again, it still has those 3 smooth pieces, C sub 1, C sub 2, and C sub 3. So it turns out that if you want to evaluate the line integral over C, where C is the union of those 3 pieces, all you have to do is evaluate the line integral over each piece. So you'll have the line integral over C1 of that function, plus the line integral over C2 of that function, plus the line integral over C3 of the same function. Not too bad. It's a little tedious because we've got to do it 3 times, but that's okay. Completely doable. Okay, so let's focus on that first integral, line integral over C1. Remember how this works. C1 is described by R sub 1 of t, and R sub 1 was t times I hat plus square root of t times j hat, and t went from 0 to 4. And the fact that this is not well defined at 4 really doesn't matter whenever you're doing a definite integral. So we can still use the bounds of 0 to 4 over here. So you state your bounds, that's your t equals a and that's your t equals b for this function. And then we need our integrand in terms of t. And to do that, you just have to remember that first component of r of t is x of t, the second component is y of t. So f of x of t, y of t, that's 3 times x minus y cubed. You're replacing x with t, you're replacing y with t to the 1/2. So we've got this right here, 3 times t minus t to the 3/2. So that goes in right here. So that's our integrand in terms of t. And then the last part we need, the last piece, is we need ds in terms of t. Now remember what ds is. It's a tiny distance. Is that tiny speed times time? Or I guess it's a speed times a tiny time, actually. So we just need the magnitude of r prime of t. So, and we're using r sub 1 prime because we're talking about that first curve. So r sub 1 was t and t to the 1/2. So when I take the derivative of that, I take the derivative component by component. So I get 1 and then 1/2 t to the negative 1/2. And then I want the magnitude of that. So I take the components, I square them, add them, and take the square root. So I get 1 plus 1/2 squared is 1/4. And t to the negative 1/2 squared is going to be a t to the negative first, so that can go in the denominator. If you want to, you can get a common denominator. Write that 1 as 4t over 4t. And so we'd have the square root of 4t plus 1 in the numerator divided by square root of 4t, which is 2 times the square root of t. It's kind of ugly, doesn't simplify very nicely, but that's the magnitude of r sub 1 prime. ds is that times dt. So you sub that in. And I guess I could write this square root of t in the denominator as t to the 1/2. So this is our f written in terms of t, and that's our ds written in terms of t. And this does simplify a little bit. You could bring this t to the 1/2 up to the numerator and then distribute. Let's see what we get when we do that. So we want to evaluate the integral now. That requires doing a little bit of algebra. So first of all, I'll bring that 3/2 outside of my definite integral. And then I've got t minus t to the 3/2 times t to the -1/2 times this square root. And if we distribute, let's see what we get. So I'll have a t to the 1/2 minus t times the square root of 4t plus 1 dt. It's a little bit better, but it still doesn't simplify very nicely at all, does it? Yeah, I don't think I want to evaluate this integral. I think we could probably use integration by parts, but that would take us away from evaluating line integrals. So this is what you would do, but I'm not going to do it. I made up this problem and it doesn't work out nicely because I made it up myself. So let's not evaluate this. But we could probably using integration by parts. We're just not going to take the time in this video to do that. Okay, so we've got our first line integral, and then we want to find the second line integral and the third line integral, also in terms of t, when we're on C2 and C3. And actually, these are going to be really nice and simple because on C2, x is just equal to 4, and on C3, y is just equal to 0. So it's going to be a very simple integral over here for these guys. This one happened to be complicated because of that square root. So we've got the line integral over C2 of 3 times x minus y cubed ds. And C2 is given by this piece, or this smooth parameterization, r sub 2. It has components 4 and 6 minus t, where t ranges from 4 to 6. And what happens at a single point really doesn't matter, as long as it's a jump discontinuity, as long as that function is not, like that curve is not going off to infinity or negative infinity or something like that. So we can still integrate from 4 to 6. That's going to be fine. So we substitute the appropriate bounds. That's our a and that's our b. And then we write our integrand in terms of t. Well, the integrand is just 3 times x of t times y of t cubed. And if we're on this curve, x is equal to 4 and y is equal to 6 minus t. So you could distribute the 3 if you wanted to. Not too bad. So that is our new integrand. And then the last thing that we need over here is that ds in terms of t. It's actually really nice and simple. Oops. So remember, ds is just the magnitude of r prime of t times dt. And r prime, we use r sub 2 prime, just the derivative of that. Derivative of 4 is 0, derivative of that is -1. So obviously the length of that vector that points 1 unit down in the y direction is 1. So ds happens to be dt in this case. And that actually makes sense from the way we parameterized it. So every second, we're going to move 1 unit in time. It's like a speed of 1 second per second. Or 1 unit of distance per second, sorry. Okay, So ds and dt are the same, so you substitute that in up here. And that's it, and you just evaluate that integral. And that integral is easy to evaluate using u sub, but we're not going to evaluate it. You can do the u sub at home if you want to, but we've set it up correctly. Okay, now let's do the third one. Got 3 times, x minus y cubed ds. That's our line integral. And now we want to evaluate the line integral over C3. And C3 was given by this piecewise smooth parameterization. So we'll evaluate the integral from 6 to 10. So we find the appropriate bounds, find our a and b. Then we want the integrand in terms of t, the original integrand. So we want f of x of t, y of t. That's 3 times x minus y cubed. In this case, x is 10 minus t, and y happens to be 0. Well, that's nice and easy. We could distribute the 3 and we get 30 minus 3t. That's f in terms of t. If you're saying to yourself, why can we do that? Again, if f is equal to 3 times the quantity x minus y cubed and we're on this curve, x is given by 10 minus t and y is given by 0. So I'm just writing it in terms of t, but it's exactly the same thing. We're just saying when we happen to be on the curve, that's what it is in terms of t. Okay, so we got our f in terms of t, and now we need our ds in terms of t. And ds is pretty easy. It's just the magnitude of r prime of t times dt. And we'll use r sub 3 because we're on our third piece of our piecewise smooth curve. R sub 3 was this very simple linear parametric function. When I take the derivative, I just get -1 times I hat plus 0 times j hat. Not much going on there. Obviously, the length is 1. So ds equals dt again, because we're going 1 unit per unit time. When we're on this curve, and that was because of our choice, because we let t go from 6 to 10, and we let x equal 10 minus t. We wanted x to change by 4 units when t changed by 4 units. You could go faster or slower on this, but then you're not going to have that slope of -1 that we have there in that relation between x and t. But because of the way we chose, ds and dt happen to be the same thing. Okay, so this question was about an original line integral. We said, find the line integral over C of 3 times x minus y cubed ds. And it was the line integral over C1 plus the line integral over C2. And I'm putting dots there because I don't want to fill in all of the details. But the line integral over C1 happened to be the integral from 0 to 4 of, let's see, it was this. T to the 1/2 minus t times that square root. And the line integral over C2 became the integral from 4 to 6 of 12 minus 3 times the quantity 6 minus t quantity cubed dt. And then the line integral over C3 happened to be the integral from 6 to 10 of 30 minus 3t dt. And that can be evaluated with a U substitution. That's just a simple power rule. And this may be integration by parts, but it was going to be too tedious for this video. Okay. So now we know how to find the line integral of a scalar function. We know that one application of that is to find the mass of a wire with a given density. And all of this hinges on the ability to find a piecewise smooth parameterization of a curve C. Let's do one piecewise smooth parameterization in 3 space, and then we'll end this video. So let's say you start here at 0, 0, 0. And then you go over here to x equals 1, y equals 1, z equals 1. In order to sketch that point 1, 1, 1, I'm going to make a little box. Oops, it's not y, that's a z. Say I'm going from 0, 0, 0 to 1, 1, 1. And then I want to go from 1, 1, 1 back to 0, 1, 1. And then let's go down to x equals 0, y equals 1, z equals 0. So our curve is this curve, the union of this curve with this curve and this curve. So I'll call that first curve C1, the second curve C2, the third one C3, and that's our C. In C1, I'll make the one from 0, 0, 0 out to 1, 1, 1. C2, I'll make that next little line segment. And then C3 will be the third one. The principle is exactly the same as it was in 2D. You just need a smooth parameterization of each of the pieces. Well, we don't have to. I always like to imagine some particle traveling along that curve. So my piecewise smooth parameterization always has pieces that sort of link up. You're starting from here to here, and then you pick up where you left off and go from there to there, and then you go from there to there. So R will have 3 parts. R sub 1 of t for t between 0 and some value. You don't have to start at 0, but I think it's easiest if you start at 0. R sub 2 will go from that value, let's call it A, to B, and R sub 3 go from B to C. Okay. So for C1, we're in 3-dimensional space, so R sub 1 should have components x of t, y of t, and z of t. And notice x increases by 1, y increases by 1, and z increases by 1. With that in mind, it makes sense to let t go from 0 to 1, and let all 3 of your variables equal t. As t goes from 0 to 1, x, y, and z are all the same, like they will be as you travel along this curve. And x is going from 0 to 1, y is going from 0 to 1, and z is going from 0 to 1. So that's a good parameterization for that little piece. For the next piece, Want the same thing. Notice we're traveling 1 unit of distance. X is starting at 1 and going to 0. So let's make that strictly less than. Let's go from 1 to 2 here. Since we're going 1 unit of distance, let's do that over 1 unit of time. And the first thing you want to do is the easy part. So you say to yourself, are there any variables that are being held constant on this line segment? Well, I'm starting at 1, 1, 1, and I'm going to 0, 1, 1. Isn't y equal to 1 the whole time there? Hope you said yes. Z is also equal to 1 the whole time there, so that's pretty simple. Y and Z are both equal to 1. And X goes from 1 back to 0. So I'll make my little chart. As T goes from 1 to 2, X goes from 1 to 0. Notice that if I add those together, I get 2 every time. X plus T equals 2. So X must be 2 minus T. So we're good there. And then for R sub 3, we want to do the same thing. So you're asking yourself, are there any variables here that are being held constant? We're going from 0, 0, 1, 1 to 0, 1, 0. It looks like X is at a constant 0 the whole time because you're in the XZ plane. That makes sense. And Y is at a constant 1 the whole time. So X is 0 and Y is 1. And Z is going from 1 back to 0. Now, since Z is changing by 1 unit, let's let T change by 1 unit. Let's go from 2 to 3. And as T goes from 2 to 3, we want Z to go from 1 to 0. So we end up with Z plus T equals 3, or Z equals 3 minus T. So my piecewise smooth parameterization of C, which is the union of C1, C2, and C3, can be written this way. Whoops. Okay. Now let's say somebody asked you to find the line integral over C of 4 times x times y times z ds. Well, then you just do the line integral over C1 plus the line integral over C2. Oops. Plus the line integral over C3. And each of those is pretty simple because these are pretty simple functions. So let's look at C1. On C1, we've got R sub 1 is t. And we're integrating from 0 to 1 in that case. We need 4x times y times z entirely in terms of t. Well, x is equal to t, y is equal to t, and z is equal to t. So this is 4 times t times t times t, so that's t cubed. That's our integrand. And ds is the magnitude of r prime of t times dt. So we want the magnitude of the derivative of that. The derivative is just a vector with components 1, 1, and 1. So you take the components, you square them, add them, and take the square root. We just get square root of 3 times dt. So the line integral over C1 is the integral from 0 to 1, the new integrand, times ds, which happens to be square root of 3 dt. and that's easy to integrate. C sub 2, C2, that's similar. We're on the interval from 1 to 2. So we're going to integrate from 1 to 2 over here. 4 times x times y times z is 4 times 2 minus t times 1 times 1. So that's just 8 minus 4t. And ds is the magnitude of r prime of t times dt. But r prime is just -1 times I hat, so its length is 1. So we just get dt. So you replace your integrand with that function of t, and then this is your ds. And then we'll do the same thing for C3. Oops, that's C sub 3. C sub 3. And in that case, x was 0, y was 1, and z was 3 minus t, and t went from 2 to 3. So we'll evaluate the integral from 2 to 3 of our new integrand, which is 4 times 3 minus t, or 12 minus 4t. R prime of t is this very simple vector, length 1 pointing down in the z direction. So ds is just the magnitude of that vector times dt, so we just get dt. And we have that right there. So the line integral over c of 4xyz ds is just the sum of these 4 integrals, or excuse me, 3 integrals. And each of these integrals is easy to evaluate. That's just a power rule. We've got our constant multiple rules, and it's very, very simple integration, Calc 1 style. Okay, so that's how we evaluate a line integral.